Morning, folks. This is lecture 14 on February 28, 2023. So, the agenda for today is discuss uh, the generalization of the viscous damping to two other cases, namely Coulomb damping and structural or hysteresis damping. Now, these two, the first one is fairly well established. Basically, for the last maybe 6 weeks, we have been dealing with the viscous damping, and we also talked about the concept of uh, uh, dry friction or Coulomb damping. However, we didn't do much about it. One thing we realized is that the governing equation in Coulomb damping is nonlinear. So, would it not be a, a good idea if we can somehow come up with an equivalent energy dissipating mechanism equivalent to a viscous damper so that instead of fooling around with the Coulomb damping, we can use this information in order to solve it as a viscous damper problem, which is entirely linear and we know everything about it. And in item number 3, we also look at the material or hysteresis damping, where there is no dry friction, there is no actually literally dashpot involved, but because of the sliding of uh, you know atoms on each other uh, within the material, energy is dissipated. We will get to that at the very end. So let's move on. First, let's concentrate on actually the viscous damper, something that we know what it is because the force in a viscous damper, which is resisting the motion of a mass, is proportional to the velocity. That much we know. But what we want to know, we want to quantify it in a different way. In other words, suppose that mass was subjected to a harmonic load of a given frequency. So uh, this mass is going to go in cyclic motion. So what you want to know is how much energy is actually consumed by the damper, or how much energy is lost during one cycle, assuming that we have a viscous damper setup. So one cycle, so to find the work done on energy during one cycle, we take the force of the damper times displacement. Now remember, this is the stuff from physics 1. Work is equal to force times displacement. Think about it like that. Now, because this goes over one cycle, and one cycle is going to be 0 to the period. Now remember, the period, this on this mass, we have a force acting with that frequency. This is the driving frequency. So the period of that cyclic motion is 2 pi over omega. So this is one cycle, okay? And the force of the damper is Cx dot. And of course, there is dx here, but uh, I'm going to rewrite dx as dx dt because I know how to integrate with respect to t, but to do it like that is a bit more complicated. So basically, we have integral over one period, c x dot squared, because it's x dot times x dot is x dot squared dt. Now, we are assuming that this x, this mass, moves in a sinusoidal manner, harmonic manner, with a frequency omega. That's what I initially said, okay? Now, can you, if we know what the x is, x dot, of course, is going to be omega cosine, omega x cosine of omega t. So if you take this, you differentiate it, stick it in there, you're going to get c omega squared x squared, because these do not depend on time, but cosine omega t squared does. Now, this is the kind of thing that you did in your calculus class. Use the half angle formula to write this thing in terms of cosine of 2 omega t, stuff that you do, or check it out in a table of integrals and work it out. This thing will come out to be pi c omega, frequency of the damper, not the damper, frequency of the applied load, times the amplitude of the motion, x squared. So for a viscous damper, The energy lost in one cycle is proportional to frequency and proportional to the amplitude square. Now, this makes sense because the faster this mass goes back and forth, the more energy is going to be lost by the damper, or is going to be consumed by the damper out of the system, okay? And the bigger the amplitude of the vibration, of course, there's going to be more energy lost. Okay, now we want to do the same kind of a thing for a Coulomb damping situation. So, first of all, if we are assuming Coulomb, remember Coulomb means that on the surface there's friction between between the two surfaces, the block and the ground, and integral over one cycle, just like here. Uh, so what we do is force the damping force for Coulomb damping. If you go back to your notes from viscous damping, you see that there is proportional to the uh, uh, coefficient of kinematic friction and the weight or the reaction force mg times the direction of the velocity. Okay, now notice that this thing, one, two, three, four terms, actually is your FD in Coulomb damping. This dx, I wrote it as x dot dt, the same trick that I used up here, and I will give you an explanation of why the answer will come out to be what I'm going to give you on the next slide. But for now, uh, this is the force of the Coulomb damping Coulomb friction, okay? And this is your dx, exactly like what we did up here. And if you work it out, under this kind of a applied sinusoidal load, which results into this kind of a steady state motion, okay, it's going to come out to be this. Now, I'll show you in the next slide why uh, this falls out of that. It's fairly straightforward. Now, what we're going to do later on, we're going to set this equal to that. If you want to find an equivalent viscous damper, we're going to say this is the same as that. And therefore, out of that, we're going to find a C based on solving for that, which is going to be our equivalent viscous damper for Coulomb friction. Now, that's what I mean. Equate these two, and we're going to solve for C equivalent. So from now on, if we have a Coulomb damping dry friction, we can replace it with a viscous damping with that equivalent uh, uh, viscous damper coefficient. Now, remember, this is going to be an approximation because we know that these two are not the same. But to eliminate the nonlinearity in solving Coulomb damping problems, Coulomb friction problems, this is a trick that we're going to use. Okay, so now I wanted to explain to you why is it that I got here 4 mu mg times x. Let's go back to this drawing. Notice that if the block is moving with this motion, okay, and it's, let's say hypothetically it's going to the right, okay, so the friction points in the opposite direction. So in going from one extreme to the other extreme, from here, okay, from here, if the block moves to the right, it's going to traverse a distance of 2x with a constant friction of mu f, okay? And then when it goes back, it's going to be mu f acting to the left. So it's right here, the position of x as a function of the friction force mu f, which is mu mg, because f is mg, mu f is going to be negative because it's pointing to the left over a distance of 2x, like that. And then when it reverses direction, it's going to go from that point to this point, which means that the friction force is going to point to the right, and therefore mu mg is positive. Okay? So if you look at the work done, this is the friction coefficient times distance of 2x, and then it goes back another mu mg times the distance 2x, and you add them up, you get this. Essentially, just remember, it's the area of this rectangle. This is going to become important later on when we talk about hysteresis damping. Okay, so it's the area of the force FD, damping force, versus X. Now, If instead of FD, we do FD for damping force plus, or friction force, think about it like that, friction force plus uh, uh, friction force plus the spring force, okay, then all we have to do is to raise this point by the amount kx, okay? Just think about it. I mean, if you see here, this is the plot of FD versus X. If you want to do FD plus KX, FD plus force of the spring, this is the force of spring, then it's going to be this point raised up by the amount KX, this point raised down by the amount KX. So that rectangle becomes a parallelogram like that, but the area of it doesn't change, okay? So that just keep that in mind. Now, remember, the idea was to equate these things, all right? The idea was to equate these things, and that's what we're going to do. And we saw for C equivalent, and we're going to get C equivalent equal to this expression. Okay, this is called the equivalent viscous damping coefficient for a Coulomb damper. So if we take this to be the ultimate story, of course, as an approximation, our linear equation, our equation of the mother of all equation becomes the same linear equation, and we can solve it, although we are dealing with Coulomb damping. Okay. Now, obviously, when we do these problems, because from this point on, if we take this, then we're going to be using a viscous damping calculation that we did in the past 6 weeks. You need the equivalent viscous damper, everything. Oh, sorry, the critical damping 2 square root of mk. Okay, that's same thing, but the damping ratio becomes this thing. This is the uh, what we get for viscous damping equivalent of Coulomb, and then it's going to be divided by the critical value, which is 2 root mk. And if you work it out, you're going to get this expression. Okay. Now remember, for viscous damper, that's all we have. But here, we don't really have a viscous damper. We have an equivalent viscous damper with this number. So that goes in here, divided by that, and you clean it up. You have to clean this up. I mean, this is not obvious from here to there. It's easy if you just write things down, because remember, omega n is root of k over m, okay? If you do it and clean it up, you're going to get this expression. Now, uh, what essentially we have done is that we have replaced a dry friction problem, a Coulomb friction problem, with an equivalent viscous damper where the area, or where the amount of energy, consumed by that equivalent viscous damper is the same as the area of that triangle or rectangle that I showed you. Okay? So if you want to do Coulomb damping, this is going to be messy. This is a nonlinear problem. We can't do it analytically. It's going to be very tough to do it. But we replace this Coulomb damping with an equivalent viscous damper. So I divided by m. Wrote it in the standard form. Okay, you could have left it like that, but I divided by m, wrote it in the equivalent form, or standard form. And when you do that, this zeta, is that number. Okay, and this equation is entirely linear. We know everything about this. We have solved it over and over for the past, well, it would have been past 3 weeks actually, because we did force problems in the last 3 weeks. Okay, so if you want to do this, we can go ahead and write all the formulas that we know in terms of this psi equivalent. Remember, we had the closed form solution, which looked like that. What I have done is that taken our knowledge from the viscous damper and replaced wherever I saw zeta equivalent, okay? And if you do that, you're going to get this, okay? You just literally, I suggest go back and see what the formulas were and plug in zeta equivalent, uh, which was this, and clear it up. Okay. A couple of things. Notice that first of all, when you look at this phase angle, if r if r is less than 1, if you work it out, now I haven't done it here, I haven't written this thing in terms of r, but it's very easy to write it in terms of r. I haven't done it though. But it shows you that if r is less than 1, in other words, the driving frequency is larger than the natural frequency, this is going to become positive, theta is positive, otherwise it's going to become negative. And uh, notice that theta and f naught, these things, sorry, theta for the given f naught, because f naught is given to us, it's actually this thing, uh, this little f naught times m, we know what it is, okay? It's the same notation that we have used before. They're of, uh, independent of for a given f naught and mu, this is independent of the frequency. There is no frequency here, okay? There is no driving frequency here. Whereas for the viscous damper, we did have the frequency popping up here. We did have R popping up here, not for uh, this model of equivalent viscous damper. So this is a very important observation because that was not the case. Theta did depend on the driving frequency. It had an R in it, okay, but not here. This is written for your observation again one more time. There are several important differences between what we got up here in this red box and what we had when we looked at the true viscous damper, okay? One of them is that notice that when R is 1, big X becomes infinite. Now, this did not happen when we had viscous damping uh, in the first in the last 3 weeks. X always never went to infinity unless damping was 0. Okay, so this is a significant difference between what we had for the true viscous damper and the equivalent viscous damping for Coulomb problem. Okay, this didn't happen. Also, also there is a discontinuity. There's a discontinuity in the phase angle. In other words, see plus or minus. See that plus or minus? We never had a plus or minus type thing before. For if you look at the phase difference plot for viscous damping, it started at the bottom, it went to 90 degrees, and turned around, and it went to pi. Okay, so that does not happen. There's a discontinuity in the phase angle. Okay, so these are the main differences. There are a couple of other ones, but these are the main differences between uh, what we have arrived at by taking a Coulomb friction, dry friction, as an equivalent viscous damper. Amplitude becomes infinite when r is equal to 1, which means that resonance, and the phase angle is discontinuous. It suddenly jump from a positive value to a negative value. The other thing is that for all of this to make sense, first of all, this under the radical must be a positive number, or over here. If under the radical is not positive, this is all garbage. Okay, so for us to be able to actually take a Coulomb damping friction or Coulomb problem or a dry friction problem, these are all the same thing, and come up with an equivalent viscous damper, this under the radical must be positive. So this is a condition that you need. Otherwise, whatever you're doing is not going to work because under the radical is going to be negative and this whole thing falls apart. Okay? So it says that the applied force, F naught, this is the, remember, this is the amplitude of the applied force must be bigger than mu mg. Of course, this must be bigger than 4 over pi mu mg, but it's including being bigger than mu mg. Okay, so it says that the applied force must be larger in magnitude than the sliding friction force. Sliding friction force is that mu mg. okay? So it says F naught must be bigger than 4 over pi mu mg, which means automatically it's going to be bigger than mu mg. Okay, so let's do an example here. I'll take a break. I think I lost my voice here. I'll take a break. Just bear with me for a second. We'll come back. Okay, let's move on. So what we have here is a block sliding on a surface which has a friction between the two. So automatically we are going to be solving a this is says it's a unlubricated steel on steel, and we're going to be solving this thing as a Coulomb damping problem, cool dry friction. However, we're going to turn it into a viscous damper by the stuff that we learned a minute ago. So the mass, let's see now, the stiffness of the spring we have, by the way, this is a common symbol to indicate that we have a dry friction. This is dry. Now, of course, we're going to replace this with a viscous damper with that equivalent value, but this is the symbol for dry friction or frictional damping or Coulomb damping. Okay. Now, what do we know here? We have the stiffness of the spring. We have the mass, 10 kilogram, and the force that is applied here back and forth has an amplitude 90. This is your F naught, big F naught, and the frequency of the driving force is 25 hertz. So back and forth, 25 hertz. Now, this point 3 comes from a table in Inman, so you can see that steel on steel, unlubricated, kinetic coefficient of friction is this. That's what we're going to need. And this whole thing makes sense as long as we meet that condition. We have to meet this condition, otherwise this is all nonsense. So we plug in the value for mu is given 0.3, mass is 10 kilogram, g is 9.81, and F naught is 90 Newton. And if this is true, then yeah, okay, we whatever we do makes sense. So this is fine. So the approximate solution to our viscous, the approximate solution to our Coulomb friction problem, dry friction problem, is going to be according to the following recipe. First of all, we have the driving frequency, which is converted into radian. The natural frequency, just plug it in, K over M. This is all given to us, 10 kilogram, etc. Now, based on that, we can find the R because you're going to need the R. Remember the formula, in the formula, there was an R, okay? So it's going to be approximately 4. This was the formula. We plug in R equal to 4.05, okay? And uh, let me see now. The only thing that we don't, this thing, yeah, this thing is going to come out. This is the amplitude of the vibration of the mass, okay? So we're calculating the X here and plugged in everything that we know, and this is the number. Now, we already checked to make sure that this is positive, otherwise this is all nonsense. We already know that, okay? That was the objective of that problem, find the amplitude of the vibration of this. If you assume that the actual dry friction problem is replaced with a viscous damper. Now, this is an approximation because in real life, if you do that, you will not get exactly the same thing, but you will not get the same thing, but exactly the same thing, and it may be close in, so this is what we came up with. Okay. So this is the second problem we are doing. It says the oops, this should be a mass spring system is subjected to Coulomb damping or dry friction. So we have a metal to metal or surface to surface contact. We don't know what mu is. We want to estimate it actually based on the information that's given to us. A harmonic force of amplitude 85 Newton is applied. So we're going back and forth with F naught sine or cosine omega t. Omega is 5. This is the driving frequency. F naught, the amplitude of the force is 85. Okay. And the amplitude of the oscillation of the mass, okay, this is the amplitude of the force applied. This is the amplitude of the oscillation given to us. This is the big X, 75 millimeter. From that, we want to calculate the coefficient of kinetic friction. Okay, we have the stiffness and we have the mass given to us in these numbers. Okay, so these are given. These are given. Okay, except 5 hertz are converted to radians per second. and we go to our equation, which relates all of these things together. The only unknown here is mu. So we have let's see now, we have omega, we have omega n, we have r. So you just plug things are, plug things in. So we have omega here, omega n, natural frequency, and you have the r, the frequency ratio, and just plug it in and solve for mu. Now I was too lazy to do this, so I used MathCAD worksheet. I wrote everything down. This equation has to be solved in terms of mu, okay? And in MathCAD, for me, it's very easy. You just write down an initial guess for mu because it's a nonlinear problem. Think about it as a nonlinear problem in terms of mu. Everything you know except that mu you don't know, but it's nonlinear. You can see that. So in MathCAD, you just give it an initial value for mu, and then it says, hey, solve it for mu approximately, and it comes out to be 1.282, which is uh, yeah. So there we are. Okay. Now I do realize that if you have to do something along this line, this on the test, it's going to be very laborious. So I definitely do not expect you to be able to do this in a short period of time on the test. But you have to know the concept. I can ask questions about the concept, but not specifically find the value of mu. Okay, so there is an observation. Let's go back to that viscous damping. Now remember, we started with viscous damping. I showed you what the energy dissipated per cycle was. Okay, but I want to go back to that and show you a couple of things because this leads us to where we want to go. Now, uh, let me remind you that for a viscous damper, this is the total force acting on the mass, right? This is the total force acting on the mass. This is the spring force. This is the damping force. These are the things that resist the motion of the block. Okay. Now, let's let's suppose that actually the motion is under uh, as in the past, steady state uh, harmonic load force of a given frequency, which automatically leads into steady state motion. Okay, a steady state motion of the block. Remember, you must have applied a sinusoidal force with that frequency in order to get this kind of a displacement. So, uh, all right. So if you take this x and stick it in there, obviously you're going to get kx, which is cx dot. Cx dot, this is x, steady state solution, steady state motion, x dot, you just work it out, you get this. Now, when you do some algebra, in other words, based on this f and that x, you do some algebra, you can show that f is equal to kx plus or minus this. You might say, wait a minute, oh, is this obvious? The answer is no, it's not obvious after algebra and trick. So let me show you actually how things work. So we have this, you understand. This thing you understand. I just took that x and stick it in there. Differentiate this, stick it in there. This you understand. Now notice what I've done here. I've written kx back, cx omega back, and cosine from trigonometry is 1 minus sine squared omega t. Cosine of omega t is the square root of 1 minus sine squared omega t. Okay, now, but if I take this x inside, if I take this x inside, there's going to be x squared times 1, and there's going to be x squared times this. That's what we have done. Take the x, big X inside, that becomes x squared multiplied by 1 and multiplied by sine squared. And notice that when you multiply, this thing is actually little x squared. There we are. That's what it is. So I'm sorry, some of these things are not obvious, but you, I mean, it has to be worked out. And we're not going to do these derivations for every single concept that we discuss. But if you want, you have to go and check it out. Now, If you take this, here's F equal to this. There we are, right there. You see that? See right there. If I take Kx to the left side, if I take Kx to the left side, Kx to the left side, and square both sides, the square root is going to go away, and we're going to get this. You take F minus Kx, square it, you get basically F squared, 2kx times f, which is right here, and then do a cleanup, you get this, okay? So from here, based on that assumption, you end up with this. Now, I already told you what happened. This goes to the left, square both sides, you're going to get this. Okay, if I plot F, big F, which is the total force, damping force, spring force, versus X, remember, for the Coulomb damping, we came up with a rectangle which was distorted, it became a parallelogram. For viscous damper, it's actually an ellipse. This is the equation of an ellipse if the vertical axis is big F and the horizontal axis is little x. This is a rotated ellipse. Now, this ellipse is called the hysteresis loop, okay? And you can think about it like that. As you increase the force, deflection increases, but as you decrease the force, displacement decreases, but not along the same line, not along this. And that's why this is called hysteresis. I mean, notice that we're used to saying increase the force, displacement increases, reduce the force, and it exactly goes back to where it was and along the same path. But not if there is hysteresis involved, okay? Apparently there is hysteresis here. Now, if there is no damping, this area, if there is no damping, this area is zero. That means then you go along the path, you come back. But if there is a damping, there is energy dissipated, and this area is going to be actually the energy dissipated in one cycle. Okay, now, this is called, this kind of a behavior is very common. For material, you load it and unloaded, they don't go on the same path. And if you do this thing repeatedly, stress versus strain is going to be a bunch of, curves inside of each other within experimental measurements and things like that. So you get some kind of a region inside that they will not be ellipses. They may look like ellipses, but they're not. But for the case of viscous damper, it is an ellipse. Okay. Now the question is, why did I tell you this is a rotated ellipse? Because you may not remember from high school, you know that the equation of ellipse looks like that. But by the way, this thing is ax squared plus by squared equal to a constant. A constant x squared plus a constant y squared equal to a constant. It looks at this is exactly the same thing on the top. It's just that I've multiplied it by a squared b squared. Now, what if in here I have other stuff? I have the product of x and y, I have dx, I have ey, etc. Then this becomes a rotated ellipse. So if you have something like that, just x squared and y squared, you have an ellipse. Horizontal, vertical, horizontal axis lined up with the major axis here, and vertical with minor. But if you have other stuff hanging around, then of course you're going to have a rotated ellipse. Okay, so here is where we go and talk about internal damping or hysteresis damping or solid damping, material damping. These are all the same thing. Okay, so they exhibit a behavior like this. You know that from your strength of material course or deformable bodies from materials course. So you load it and then you unload it. It goes, you load it up to a point, it goes elastic, and then it yields, and then it goes, for example, horizontal. As long as it doesn't fracture, you don't go all the way to a fracture, and then unload it, it goes linearly, and then it repeats. This is called hysteresis loop, and it happens in material. Okay. Now, experiment has shown that if you do this thing based on a sinusoidal loading, because you put the sample in the machine and you can make it go apply a sinusoidal load to it or a displacement, either way, okay? That does not depend on the frequency. In other words, regardless of how fast you do it, you get the same kind of a behavior. Experiment has shown that it's independent of frequency and is proportional to square of the amplitude, which means big X squared, okay? This area is proportional to omega, proportional to big X squared and the K, the stiffness, okay? So basically, I'm saying that experiment has shown that delta E, the area of this, is proportional to the uh, uh, independent of omega, independent of omega, no omega here, okay? Proportional to stiffness and big X squared. Proportional means that there is a factor beta here, okay? We have to, this is called the hysteresis damping constant, okay? If you know that area, you know the stiffness, basically the slope of that line or that line, and you know the amplitude of the oscillation that you can actually record, you can find the value of beta, by the way. Okay, this is called the hysteresis damping constant. Okay, good. Just be careful that some books put the K and beta, not ours, K and beta together and call it H. We're not going to do that. We're going to, Inman uses exactly this notation. We're going to use this. Now, so if we have material damping and we have experimentally that curve, that loop basically, how do we replace that with an equivalent viscous damper? Well, we're going to use what we know. In other words, we know that this is from experiment, okay? And we're going to set it equal to, if you're going to say that this is this equivalent viscous damper, then remember for viscous damper we had pi, we had c, omega, x squared. You equate these things and solve for c equivalent, and there we are. There we are. Okay. So another way to look at it is that omega is under your control, uh, k is under your control, and you know beta, and you just take that stuff and put it in there. You might say, how do I know beta? Well, it comes from here. You know that area, right? Delta E, you know. That is the area of that hysteresis loop. You know K, you know X, you find beta if you want. K beta, you know, right there. Now, the good thing is that this is a linear equation that we have worked in the past 3 weeks with, just like the trick that we used for Coulomb damping. We did exactly the same thing, except that for Coulomb damping, this was, something else. So we know the solution to this. Go back your notes, please. Okay, we're going to get that. And you have the information here. If you go back and identify every single one of these with every single thing that we had for X and phi, etc., you're going to come up with these. So these are the equivalent viscous damping solution whenever you have to basically give up your material uh, material damping or hysteresis damping and replace it with simpler situation. This is going to be an approximation, of course. You just keep that in mind. And also, all of the stuff that we have done today is assuming that the load is applied harmonic. Okay, so none of this stuff makes sense if you actually went and did something which is not under harmonic load. Okay, so this is very important. Harmonic load at a given frequency that you see here. By the way, I've plotted here certain things that look similar to what we did before. These look similar to what we did before. Now remember, for Coulomb damping, this went all the way to infinity at R equal to 1 shot. Remember the fundamental differences? The two of them was that there's a discontinuous jump in the case when we replace a Coulomb problem with equivalent viscous standards, discontinuous jump. And also at R equal to 1, this shoots to infinity. Now, obviously, that doesn't happen in material damping. This is a more realistic way, for example. Let's do an example. So here's a situation. We did an experiment of the material. Okay, so this is what we got. Force deflection curve out of the machine came. You get a hysteresis loop like that. This area, if you estimate it, suppose it came out to be 5 Newton meter, of course, just count the number of rectangles or squares if you want. And there's a slope. The slope of this line, which is the stiffness of the system, is 50,000 Newton per meter. And the max, this is the maximum deflection. This is the big X. This is your big X. Okay. So what we want to do is the frequency of calculate the equivalent viscous damping coefficient for 2 Hertz driving force. Okay. It's interesting. You will see that this actually we'll see how it comes out. And then it says plot that equivalent for any driving frequency in this range. Okay, so it's written here for you. Omega is given to you 62.83. This area is is dissipated energy area, and we know that uh, for uh, for material damping, this is what you got. Okay, so we're going to replace that. We're going to replace that. See that for material damping, this thing is independent of omega. There is no omega here. There is no omega. Okay, this is 5. That's this area. We know the value of K. You know the value of K, and uh, you get your deflection, maximum deflection. Just look at this, is big X, which is 0.01, and out of that you can find K beta. Okay. Now, if you want K beta, this is fine, but if you want beta, obviously you have to know the value of K. But I don't need specific the value of beta. What I do need is K beta. That's going to be good enough. So we found this, put it there. Omega equivalent. It had an omega at the bottom, right? And 62.83, and this is the equivalent viscous damper, and there we are. Okay. Now, when I say there we are, it says the second part of the problem is that plot that plot that equivalent viscous damper as a function of omega. Notice that C equivalent, the omega is in it. Okay. It says if I did this thing for a different omega, what should I expect? So this is the plot that you're going to get for different values of omega. So as it becomes very fast, the application of global C equivalent becomes very small. Okay, and yeah, specifically, I don't need the value of K. Okay, but if I want to find the beta, of course, I do need the value of K. Okay, this is, I think we have 2 more examples to do. This is our next problem. The most common, this is the common icon for material or structure or solid damping right there. This thing, remember we had a common one for, of course, we have a common one for viscous damper. We had a common one for Coulomb friction or dry friction. And then this is the one for structural hysteresis or material damping. All right, what do we know here? We know that this F naught is 5,000. And oh, sorry, yeah, let's put it, if you apply 5,000 newtons, okay, if you apply 5,000 newton, we know that the block moves by that much, okay. And we have later on, this basically this information will tell you the stiffness of the spring. Okay, that's all. It says a load of 5,000 newton results in static deflection of 0.05. You have force, you have deflection, they'll give you K. Now, we now have to do the rest of the problem. It says a harmonic fall, which means this F naught is 1,000 Newton, is applied and is found to have a resonant frequency of 0.1, resonant amplitude of 0.1. So big X at R equal to 1 is 0.1. It says causes a resonant amplitude of 0.1. This is amplitude big X at R equal to 1 is this number. Okay, First of all, find the hysteresis damping constant of the structure, which means find the beta. Find the energy dissipated per cycle at resonance. This is very important. Steady state amplitude at 1/4 of the, so repeat basically this thing, except that don't go all the way to resonant, go to 1/4 of the, basically R equal to 0.25, right? 1/4 resonant frequency, and steady state amplitude at 3 times. One is for uh, R equal to 0.5, the other one R equal to 3. Okay, so let's move on. First of all, as soon as you have this, you have the value of K. That's good. Okay, now let's move on. Now notice that the mass is not given to us because everything that we're doing here is at R equal to 1. Okay, so omega n, whether we know it or not, is not going to affect the problem because R, we have it R equal to 1. Okay, because, okay, so there we are. So this is the relationship we have on slide 16. You remember that? I wrote the formulas here for the solution of the hysteresis or material damping. It looked like that. When R is equal to 1, notice that this guy goes away, and uh, we know big X, we know F naught, we know K, and we can find beta. Okay, now energy is dissipated per cycle. If you look at the equivalent viscous damper, it's going to be like that. Okay, but equivalent viscous damper, we said it was beta k over omega. The omegas cancel, right? See that? Omegas cancel, and you get this. And just plug it in. Energies dissipated per cycle, just plug it in. So you have pi, beta, we just worked it out. And this is your K, the stiffness that we found initially, and the amplitude 0.1 squared. This is at resonance. This is at resonance because it says that the amplitude at resonance is 0.1. That much energy is lost per cycle. And notice that omega just disappeared. It says energy dissipated per cycle is independent of the driving frequency, which is confirmed by the experiment. Now, it says, what if the R was 0.25? You basically repeat this whole thing. Notice that the amplitude, instead of being 0.1, is a lot smaller, 10 times smaller. And if at 3 times, also is going to be smaller than that. It's 100 times smaller. So there we are. At resonance, the amplitude is large, 0.1. That was given to us, 0.1 meter. At to the left of the resonance point, or to the right of resonance point, the amplitude is going to be several or one order of magnitude smaller here and 2 orders of magnitude smaller there. This is the last example for today. So in fluids courses, you were told that drag force is proportional to velocity squared. You remember that? Square of the velocity. So based on that observation, because based on that observation, we want to find the equivalent viscous damping coefficient. Okay, so let's hypothetically say we have something that is going back and forth in a fluid at low speeds. Now, maybe a ball or airfoil or whatever, a plate. Now we know that the drag force on this, which incidentally has to do cross-sectional area of the projection, of course, cross-sectional projection. Now, you were told in fluids courses that this drag force is proportional to v squared, velocity squared. So what you want to do, we don't like x dot squared. We want it to be proportional to x dot because everything that we know about viscous damper, cx dot, this becomes linear. So we want to find the equivalent viscous damper for this particular problem. Okay, we could just go through the same calculation that we did when we did initially the calculation for the work done and things like that. So we are told that the the friction coefficient, not the friction coefficient, the drag force, if you want, proportional to the velocity square. Remember, for a viscous damper, this is not square. This is a single. Uh, this is just a one. Okay, but there we are. Assuming that under harmonic load, these are exactly kind of thing that we did before. So you find the differential derivative of this, and you just plug it in. You take this thing and plug it in there. You get this ugly term. And now we have to do this. These all look familiar to you. And we're going to put FD here, and dx, we're going to use a trick to write it as x dx dt dt. So over one cycle. Now this is done, instead of doing from 0 over one cycle, we do it twice, going half the cycle. Or just take this stuff and plug it in. So FD is this ugly thing. Dx dt is over here. And this is where we end up with sine cube. You might have wondered, why in the world did we do this kind of a thing in a calculus class? Remember, in a calculus class, as a technique of integration, you ended up doing, of course, integral of sine and cosine. You know that. You also did integral sine squared and cosine squared. Use half angle formula, but you also did sine cube and cosine cube. Now you can see where you need that stuff. Look it up in a table. Okay, look it up in a table. That's if it's bothering you, just plug it in. Okay, you're gonna get up. This you have to either do integration by parts several times, or look it up in a table. You're gonna get this, and so that thing, if you want to find the equivalent viscous damper, this thing must be pi c equivalent omega x squared. Remember, this was for a viscous damping. We want this thing to be equal to that, and you're going to get that expression that I forgot to finish. We were asked to find, let me see for a second, something that says find the equivalent damping for such force and find the resonant amplitude. Okay, resonant amplitude. Big X, that's what we want. Big X, okay? So in order to find big X in it, we need the damping ratio, C over C critical. C equivalent we just found, it was this thing. Of course, this we know what it is, 2m omega n. Omega n is root of k over m. We already know that. But at resonance, this is equal to 1 because that big X is biggest at r equal to 1. Kind of. If you go back to your notes and test number 3, you see that that is not quite true, but it's very close to r equal to 1. The peak is very close to r equal to 1. So there we are. Okay, at r equal to 1, you just plug in these values. Zeta is there, so plug it in. Plug in zeta. That thing up there just goes in here, and just clean it off. Big X equal to square root of 3 pi f naught over this. That was the question. What is the maximum amplitude at resonance? So we were asked to find big X at r equal to 1, knowing that this is what zeta is, because we're dealing with this situation where uh, the, the drag force is proportional to the square of the velocity. Okay, there we are. Okay. Okay, let me say a few words here. This complete chapter 2, and we're going to move to chapter 3 on Thursday. Chapter 3 deals with a situation where the right-hand side of your equation, the mother of all equation, is no longer either 0, that's essentially chapter 1, or sine and cosine, which is a harmonic loading on the right-hand side, essentially chapter 2. And chapter 3 is going to start with the subject that what if the right-hand side is none of these? For example, What if the right-hand side force is a sawtooth force or a step force going between plus and minus one, okay, something like that, or maybe an impulse force. So that is essentially going to be chapter 3. Okay, good luck.